We know it's really big and really hot and really far away. We see it every day. But what is it? How big is it? And what is it made out of? Hey guys, it's Mr. Chavone. Today we're going to be talking about the sun.
So just by looking at the sun, you might assume that it's a gigantic ball of fire. And this isn't entirely correct. So the sun is not on fire. So fire is a chemical reaction that occurs when we burn things here on Earth that requires three things. You need a source of fuel, a heat source, and oxygen. Now, the thing about the sun is, even though it contains oxygen, it's going to contain a very tiny amount of oxygen. And that oxygen is actually being produced by not a chemical reaction, but by a nuclear one. So the thing to understand about the sun is it's not a burning chemical reaction, it is a nuclear reaction we call nuclear fusion, all right? So the thing to understand about all that heat and light and energy that is being produced by the sun is being produced by this process known as fusion. Now, here on Earth, we do have nuclear processes going on, or nuclear reactions that occur, known as fission. And in a fission reaction, you basically have atomic nuclei that break apart, or rather, that particles are firing out from the nucleus of an atom. Well, fusion is the opposite of fission. Instead of nuclei breaking apart, you have atoms or atomic nuclei coming together and being squeezed together under the enormous amount of heat and pressure that you find in the core of the sun. And in our star, which is kind of a middle-of-the-road star, it's average in its temperature, in its size, and the amount of heat and light it produces. It's going to take hydrogen, which is the fuel source of fusion, and it's going to squeeze those particles together to make helium. All right. So for the most part, the sun is going to be about 90% hydrogen and about 7% helium. The rest is going to be other trace elements that we find in the material of the star. Okay, but that's mostly it. So fusion is hydrogen gets squeezed together or compressed or fused together to make helium. And that's going to create a huge amount of energy. All right. Now, the thing to remember is that both of these forces need to be in balance with each other. So when we talked about fusion, we talked about the fact that gravity is squeezing in on the material in a star, and fusion is basically exploding outward. And those two forces in a star need to be in balance with each other. Gravity squeezing in, fusion pushing out, in order for the star to be stable. If one of those forces wins out over the other, it's going to have a massive impact on the life of the star. So for example, fusion, if this is my sun, fusion wants to push out on the star and make it bigger. In fact, this is what happens to some stars as they reach the end of their life cycle. Fusion is pushing out and out and out, making the star grow bigger and bigger and bigger, all right? But if gravity were to win out, the opposite would happen. The star would begin to shrink and shrink and shrink until a couple of things could happen. So when the star reaches the end of its life cycle, it either grows so big that it kind of expands and sloughs off its outer atmosphere, and you're left with what's known as a tiny white dwarf star, or the opposite could happen. You get a huge explosion, and all that material is compressed into a tiny amount of space, which we also know as a neutron star, or if the star is particularly enormous. I mean, our sun, like we said, is an average sized star. If you were to get a truly gigantic star that goes supernova and explodes, that explosion is going to compress all that material down to a single point, and we know that as a black hole. So depending on the size of the star, its death is either going to be very gentle, it's going to just slough off its outer atmosphere, or it will end violently in a huge explosion. Okay? So again, in order for the star to be stable, those two forces, gravity and fusion, have to be balanced with each other. Okay? So now we're going to take a look at some features of the sun. We're going to take a look at the three inner layers of a star, our star specifically, as well as the three outer layers of its atmosphere. Okay? Now in your book, you can see a diagram if you turn to page 549. There's a really good diagram there that kind of shows you the different layers of the sun, its inner layers, as well as its atmosphere and different features that we find on the sun. Just so you know, on the worksheet that you guys are going to be working on, it's really important to understand that there's a difference between these little loops of energy that we call a prominence, and then these giant releases of solar material called a solar flare, which we'll talk about in just a little bit. So first, we want to take a look at the first three inner layers of the sun, okay? And that's going to be consisting of the core, the radiation zone, and the convection zone. So the core, this is going to be the hottest part of the star, by far. This is because this is where nuclear fusion is taking place. So the thing that's driving all this energy, this heat and light, is occurring here at the very center where gravity is greatest, and it's squeezing and pushing all that material together, and that's going to create a huge outward force, release of energy. After all that heat and light exits the core, it's going to enter the second layer of the star, which is known as the radiative zone, or the radiation zone. And in here, you kind of have that push and pull of fusion versus gravity. And all that material is going to move very, very, very slowly through the radiative zone. In fact, scientists believe it takes about 100,000 years for material to leave the core and make its way through the radiation zone. It's going that slowly to reach the third layer of the sun's interior. We call that the convection zone. Now, the word convection is all about this swirling of gases. And the reason that you have this swirling or the circling of gases is because you have this effect where hot gases will leave the radiation zone, they'll move their way up to the sun's surface, they'll cool down, and then they will fall back down into the sun's interior, and that will happen over and over again. So as the gases cool, they fall back down into the convection zone, they get heated up, and it's just this cycle that goes over and over and over and over and over again through the convection zone. Okay, so it's basically this rising and falling of gases as they are heated up and then as they cool down. All right, so that's going to bring us back or onto the three layers of the sun's atmosphere. So just like there's three layers of the sun's interior, we're going to look at the atmosphere of the sun. All right, so this is going to also consist of three layers. All right, the photosphere, so remember this is important, photo meaning light, or the light sphere. So when you look up at the sun and you see that brilliant, bright disk of light, you are seeing the photosphere. All right, so that's the visible surface of the sun. Now, you don't want to stare too long at this because it could make you blind and burn your retinas, okay? But with special protective, say either like goggles, or different lensing techniques, scientists have been able to pick out two other layers of the sun's atmosphere. All right, so the second layer after you leave the photosphere is what's called the chromosphere. Chromo coming from the Latin word for color, and the reason it's called the chromosphere is that you're able to see this very faint red tint to this area of the sun. So in certain filters, it kind of has this red edge to it, and then out beyond the chromosphere, extending for millions of miles out into space, you have what's called the sun's corona. Now, corona just comes from the Latin word for crown, and you can see from this picture right here is a special filter. This is actually during an eclipse, where the moon has passed over the face of the sun. It's covering up the main body of the sun, and out around it, you see this corona. Now, the corona is not the hardest part, or excuse me, it's not the hottest part of the star in total. It's just going to be the hottest part of the atmosphere, which is really strange. So the photosphere is only about 5,500 degrees Fahrenheit, whereas the corona, which extends out beyond the sun, can be over 1,000,000 degrees Celsius. Okay, so again, that's not the hottest part of the star, but it is the hottest part of the star's atmosphere. So moving beyond that, we're going to talk about some different features we find on the surface of stars. So these are only things that have come to light in the past several decades of research as scientists have been able to develop better telescopes, better filtering technologies, and different types of detection. Scientists have been able to locate and define these different features of the sun. Okay, so we're going to take a look first at these really strange features. We call them sunspots. Now, a sunspot basically is just a region of cooling gas that you find on the surface of the sun. And so if you're able to filter out all that UV radiation and all the bright, brilliant light, you would be able to see that there are regions of dark, cool gas on the surface of the sun. And one of the things that studying sunspots has allowed scientists to understand is that the sun itself is spinning in place. It's rotating on its axis, all right? Why? Because scientists have been able to see these sunspots rotating on the surface of the sun, okay? So one of the things to understand, though, is that while these spots can appear really, really tiny on the surface of the sun, if you were to hold up the Earth next to the sun, I mean, the Earth is tiny compared to the sun. The sun is absolutely enormous, and just one of these sunspots can be many times larger than the Earth. I mean, they're absolutely enormous, okay? But sunspot activity kind of gives us a hint to things that are going on the surface of the sun. In fact, sunspot activity is linked to different types of activity we find here on Earth, and we'll talk about that in just a little bit. Okay, so going on to, let's see, we're on page 550. Okay, so on 550 we see there's something called a prominence. Now, a prominence is a large loop of solar material. Okay, it's not the same as a solar flare. So basically what's happening here is joining two sunspots together where you kind of find the edges of this prominence. Those are going to be sunspots, and it's going to be kind of stretching or pulling at the solar material. You kind of have, you imagine like invisible rubber bands of the sun's electromagnetic field, and this layer of plasma is going to line up along that electromagnetic band. All right, and what can happen is those prominences, sometimes they can stretch and stretch and stretch, and then they just get reabsorbed by the sun. In other cases, if that prominence stretches far enough out into space, eventually it can break off, and you get what's called a solar flare. So we can watch this here in this little animation, okay, watching a prominence grow and grow and grow and stretch until it breaks off and is actually going to fire solar material out into space. Now, if the Earth happens to be in the path of that solar flare, there are different effects that it has on planet Earth. So at times this can interrupt, say, like communications, radio, radar, telecommunications, satellites. These solar flares can have an impact, and they do work on a cycle. So there's a 7-year cycle of solar flare activity that astronomers keep very close eye on. Now, one of the things that you need to understand is that solar flare activity is also connected to something that we see on Earth. It's called the aurora borealis. If you ever heard of the aurora borealis, it's also known as the northern lights. Basically, this is going to be the cause. So as that solar material is fired out, ejected from the sun, it's making its way through the solar system, and if it hits the Earth, all that solar material is going to get caught up in the Earth's own magnetic field. All right, and it's that magnetic field that's going to protect the Earth from these solar flares. If the Earth didn't have a magnetic field, we would be in big trouble because we would get cooked by those solar flares. It would basically burn our atmosphere away, our oceans would boil, and then life on Earth would not be possible. So even though the sun is incredibly important for life here on Earth, I mean, we couldn't survive without it. We wouldn't have heat, we wouldn't have light, we wouldn't have plants, everything would die. Okay, but at the same time, if we didn't have that protective shield surrounding the Earth, our magnetic sphere, we would be literally cooked by the sun. Okay, so understanding the aurora borealis is not only do we have the northern lights, but there are also southern lights, which are known as the aurora australis. And the reason is that the bands of magnetic or ionic material extend from both directions, from the north and south pole of the Earth. And that's basically because as the Earth is spinning, we have this giant molten core or superheated core of iron. And iron is a magnetic material. When you spin iron at a certain speed, it creates a magnetic field. And it's that superheated spinning ball of iron in the core of the Earth that's actually protecting us from all that solar activity. So just a couple quick reminders. As you guys are going and doing your sun worksheet, so again, there is a really great diagram on page 549. Just remember not to confuse a solar flare, which is, I think, what's pictured there on in your book. Do not confuse that with that loop of gas, which is a prominence. Okay, so that's a big difference. So understanding that a prominence is going to be a loop of gas, whereas a solar flare is going to be that eruption. The loop is broken and it gets fired out into space. Okay, so as you guys are doing your homework, reviewing, remember you got a quiz on Friday. Be sure that you also have the PowerPoint in front of you. I think it'll be very helpful. Make sure you're doing the reading from the book. And as always, if you have any questions for me, do not hesitate to shoot me an email. All right? Cool.